So we were looking at this very important vocabulary at the end of the notes on Tuesday, and we certainly used some of this vocabulary in our solvent lab, like discussing whether something was soluble or insoluble, and the difference between the solvent, which is the liquid that does the dissolving, and the solute, which is the solid that is getting dissolved. And so now I'd like to take a little time to look into those last two vocabulary words, dissociation and solvation, a little bit more, and to think about how we can predict whether a molecule is going to be soluble in a given solvent or not. So let's look at two molecular compounds. So we have glucose here. That's one of the things that we did look at in our solubility lab yesterday. So you can pull out your solubility lab and take a look at your results from glucose. And we had paradichlorobenzene, which was one of our options that we could have looked at. I did use naphthalene instead, simply because I had more of it in stockroom. So let's decide if these molecules are polar or nonpolar. The first thing remember I have to do is decide if I have some polar bonds. Clearly in glucose, I absolutely do have polar bonds. I have carbon-oxygen bonds. Each one of these vertices on this is a carbon. And I have lots of OH bonds here. Those are definitely polar bonds. Also, I notice whenever I have a hydrogen directly connected to oxygen, that's a point where I start thinking about hydrogen bonding with these very, very polar bonds here. If I look at the overall molecule, I can see that I have three OHs on the bottom side of this ring and two OH groups on the top. So it is not symmetrical. And so this would be a polar molecule. So glucose is polar. And if I look at my solvents from yesterday, glucose only dissolved in water, which is a very polar solvent, and it dissolved maybe a tiny bit in ethanol, which is a polar solvent, but not as polar as water. And if I think about all of that hydrogen bonding that happens in water that explains all of those odd things about water, well, look at all of these options for hydrogen bonding that could happen between water and glucose. There's lots of OHs here that could mesh into that network of interactions of hydrogen bonds in water. So it explains a lot why glucose is soluble in water. Now, there absolutely is hydrogen bonding in ethanol as well, because that molecule does have an OH on the end. And so perhaps that's why it could dissolve somewhat in ethanol, but not as well as in water. Now, paradichlorobenzene does have polar bonds. I have a carbon-chlorine bond on the top and a carbon-chlorine bond on the bottom. But we can see that this is a perfectly symmetrical molecule. So I would have a dipole pointing down towards the chlorine, but I would have a matching identical dipole pulling up towards this chlorine. And so those would cancel each other out. And the symmetry of this molecule means that this is a nonpolar molecule. It's very similar to naphthalene in that it has this carbon-hydrogen bunch of rings here. So I would expect that paradichlorobenzene would not be soluble in water because our nonpolar substances were not soluble in water, but it probably would be soluble in hexane. And in fact, I can tell you from having run this lab other years using paradichlorobenzene, that is absolutely the result you would get. It is absolutely not soluble in water or ethanol, but it does dissolve well in hexane. So we could maybe turn what we learned yesterday into a little bit of a rule, a rule of thumb, we'll put it that way. Like dissolves like. It is a rough rule, but a useful rule in predicting whether one substance will dissolve into another one. So if I say like dissolves like, what exactly do I mean? Well, a polar solute will dissolve a polar solvent. So Water, for example, dissolved glucose. Water and ethanol are miscible, they mix in any percent. So two polar things can dissolve into one another. And that's because of the kind of intermolecular attractions they can have. A polar solute, even if it can't hydrogen bond with water, at least something that is polar could have dipole-dipole interactions. And so it can have some stronger interactions that could help it dissolve into the water. A nonpolar solute then generally will dissolve in a nonpolar solvent. So iodine, for example, which is I2, that's completely nonpolar, completely symmetrical, was soluble in hexane. And our paradichlorobenzene, which was nonpolar, is soluble in hexane. And naphthalene was soluble in hexane. But glucose did not dissolve in hexane because it is too polar. It needs a polar solute to dissolve because in hexane it cannot form any interactions to help lower the energy of the molecule. So it makes more sense for it to just stay attached to other molecules that it can interact with instead of trying to get out into the solution. So when you look at something, think, is it polar or is it ionic? Then it's going to want a polar solvent. And if it is ionic, it's going to want a really polar solvent like water. If it is nonpolar, then we want to put it into a nonpolar solvent so that it can dissolve. So I talked about these two processes involved in something getting dissolved. And here they are, dissociation, remember, and solvation. So I can see here, these water molecules are coming in and they are crashing into this crystal because they're going along and they're moving through the solution. They crash into the crystal, and when they crash into that crystal, they actually knock ions off of that crystal. That is the dissociation part. This works for ionic compounds, this works for covalent molecular compounds. If I am dissociating, say, glucose from a crystal of glucose, I'm actually dissociating the entire molecule off into the solution instead of just one ion at a time. This would be something like salt. Well, it is salt, sodium chloride. Once the substance has dissociated, then really what determines whether it will stay dissolved is whether or not it can solvate, whether it can form interactions with the solvent. Since this is sodium chloride in water, it can absolutely form ion dipole interactions and be hydrated or solvated by water. And that can help lower the energy of this ion by itself because it's attracted to all of these partial negative charges to kind of balance out that positive charge. And on the chloride ion, we put all of the partial positive sides around so that it gets attracted to a bunch of partial positives that help balance out that negative charge. If it is a molecular compound like glucose, then those glucose molecules would then have dipole-dipole interactions, or in glucose's case, it could even hydrogen bond with the water molecules and wrap itself up in those water molecules to help replace essentially the lower energy interactions it got from being in the solid. So dissociation first, then solvation. So if I'm thinking about an ionic solid like what we had on the last page, our polar molecule is going to smash into, our polar water molecule is going to smash into the crystal and use that kinetic energy of the collision to knock the ions off. And then the partial charges of the water will solvate the ions to help keep them apart. Of course, we know that some solids are better at dissolving than others. We have made precipitates before, so we know that some things, even if they are ionic, are insoluble in water. And so we can think about some factors that actually affect whether or not something will dissolve and how quickly something will dissolve, especially. And this is where I like to tell you that you have a tasty chance to earn some extra credit. One way you can earn some extra credit in this unit is to make some Jello and take a selfie of yourself with your Jello. And next week, when we get closer to our test, I will post a Google Classroom post where you can attach your selfie with your Jello to get a point of extra credit on your test and some tasty dessert. Now, why do I say that you can make Jello for extra credit? Well, because Jello is a great example of all of these factors that affect how quickly and how well something will dissolve. So the first thing I can do to make something dissolve faster is to make it have a greater surface area by grinding it up or crushing it up into smaller particles. And if we think about the process of dissociation and how the solvent has to come in and smash into those crystals and knock those ions off, the larger the surface area available for the solvent to come in and crash into the solute, the more collisions and the faster we can get things to dissolve. If we think about Jello, well, when you open your packet of Jello, you'll notice that the particles are just incredibly fine because gelatin is not wildly easy to dissolve. So having very fine particles means there's lots of room for the solvent to crash in and dissociate the particles of the solute. The next thing I could do to help dissolve something is something we saw in our solvent investigation lab. We agitated the solution. You can stir it or shake it. And that's definitely one of the steps in making Jello. Once you put the water in, you have to stir the Jello until all of the solid dissolves. Well, if our first one was talking about dissociation, the second one here is a little bit more about the idea of solvation. Because if I agitate the solution, I'm constantly bringing a supply of fresh solvent molecules in so that they can solvate particles after they are dissociated from the solid. So we'll constantly have fresh solvent molecules coming in to wrap up the solute particles and get them out into the solution. So agitating a solution, stirring it or shaking it, is a way of helping it dissolve faster because I'm constantly bringing in fresh solvent molecules to solvate the solute molecules. It's hard to say. And the last thing that I could do to help make a solid dissolve faster is heat. I can heat the solvent. And of course, that's the very first step in making Jello is you boil water and you use almost boiling hot water at the beginning. And that has to do with the dissociation step again. Remember, I want the solvent molecules to crash into that solid crystal and smash little particles off into solution. Well, the faster the solvent is moving, the higher the temperature is, the more energy there is in the collisions. And so the more energy there is, the more they can smash into that crystal and dissociate the ions. So a higher energy solvent is going to be better at dissolving any solute. So these factors, they're not going to make something dissolve if it is just flat insoluble. It wouldn't matter if I heated up hexane to its boiling point. I could not dissolve sodium chloride in hexane. But if it's something that will dissolve, I can make it dissolve faster and sometimes make it dissolve more by using heat, increasing the surface area, or agitation. And we can actually chart some of these factors, well, especially the heat part, on what's called a solubility curve. So let's take a look at some solubility curves. Looks like this. Here's several of them. One of the things to look at is to make sure that you are looking at the right solubility curve for the right compound. That's always important. And the solubility curve is going to express the relationship between the amount, usually in grams, of a compound that can be dissolved in a certain amount of solvent, usually 100 grams of H2O, and it relates that amount to the amount of temperature. So if we think about something that we talked about a few times before, say when we talked about ion swap reactions that made a precipitate. One of the things I talked about was the fact that you are not going to get a nitrate as a precipitate. Well, let's look real quickly at sodium nitrate here. And if we go at standard room temperature, which is about 25 C, and we go all the way up to the line, we find that we can dissolve over 90 grams of sodium nitrate in 100 grams of water at room temperature, which kind of explains why I told you that sodium nitrate was never, ever, 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 ever going to be the precipitate. And I have a similar, if not getting worse, reaction here with potassium nitrate. I look at potassium nitrate. Potassium nitrate, I can do almost 35 grams per 100 milliliters of water. 35 grams is a lot. So these are very, very soluble compounds. Other things, you can see the solubility is very low. Cerium sulfate is a generally not very soluble salt. It can dissolve less than 10 grams in 100 mils of water. It's not super insoluble like some, where I would, not even be able to see this line because it would be so close to the x-axis, but it is certainly much less soluble than some of our other substances. We can also see that some compounds are vastly more affected by the temperature of the water than others. The slope of the line on potassium nitrate is quite steep. The slope of the line on sodium chloride is not very steep. So there's a lot of different relationships we can see here. But in order to really use these, we need a couple of words again. So we're going to go back to doing a little vocab for a minute. Unsaturated, saturated, and supersaturated. So an unsaturated solution is a solution that contains less solute than a saturated solution. So essentially we could think of this as not full. Or you could think about a solution kind of acting like a sponge for the solute. So in this case, I have my sponge, I've mopped up the spill, and I can keep going. I can mop up more spill with the sponge. The sponge is not completely full, it's not saturated. Then a saturated solution is a solution that contains the maximum amount of dissolved solute. So at this point, if I were thinking about my sponge metaphor, my sponge would be at the point where if I tried to wipe up any more water, it would just smear the water around on the table. No more water could be absorbed into the sponge. That sponge is saturated. It's full. It's holding as much solute as it can. And then in some unusual circumstances, we can get what's called a supersaturated solution. Now, a supersaturated solution is an extremely unstable situation. It is overly full. It is abnormally full. It contains more dissolved solute than a saturated solution does. And so making a supersaturated solution is a matter of heating something up, cooling it down, and then don't breathe on it, don't look at it, don't let anybody bump it, don't let any speck of dust fall in it, don't sneeze, don't, you have to be so careful because any tiny little disturbance of a supersaturated solution will cause it to crystallize until it gets to saturation. So a supersaturated solution is extremely unstable. It is not something that you're going to do under everyday circumstances. It's something that is very challenging to keep at that state. So if I look back at my solubility curve, and I say I'm going to use this light blue sodium chloride as an example. So at 30 C, any amount under this line, so any amount between 0, which would not be a sodium chloride solution, but 0 and about, say, 35 or 36 grams would be unsaturated. Once I get to that 36 grams or so, I would be right on the line, and that would be a saturated solution sitting right there. If I very carefully managed to get this up to the point where it, say, had 40 grams of sodium chloride in there, it would be above the line, and it would be in that unstable, supersaturated situation. So unsaturated under the line, saturated on the line, supersaturated above the line. Always remembering that supersaturation is not a very stable situation. It's not easy to do. When we are at saturated solutions, we are at what is called equilibrium. This is the first time we'll see that. So a lot of times we'll see it next year. In equilibrium, the opposing processes of dissolving, so dissociating and solvating, and crystallizing, where the ions are solidifying again onto a particle of the solute, they're occurring at equal rates. So we actually denote that by using a double-sided arrow like you'll see here. The dissolving is happening at the same time and the same speed as the recrystallizing. And so there's no real net change, because if a pair of ions dissolves, another pair of ions just crystallizes back on. That's why a saturated solution is one single solitary value at a given temperature. When we're at that point, we stay at a constant concentration. So let's practice reading one of these curves. Okay, we have a beaker containing 80 grams of lead nitrate in 100 grams of water, so that means I can use this particular chart. And that says that the temperature is 30 C. About how many grams of salt are undissolved on the bottom of the beaker? Okay, well, that tells me that at 80 C, I am at a saturated solution. It is full, and there I'm not at a supersaturated solution, because there is solid sitting on the bottom. We're at that equilibrium where as some of the solid dissolves, some of it recrystallizes. So what I'm going to do to find out is I'm going to find out how much did I have in a full solution. So I'm going to find my lead nitrate line, which I highlighted in red. I'm going to take my 30-degree line and go up to where I meet that line. And I'm going to go across. I'm going to see that that's about 64 or 65 grams. So if the solution is full at 65 grams, say, and I put 80 grams in, well, then apparently I must have 80 minus the 65 that are dissolved sitting on the bottom. So I must have about 15 grams sitting on the bottom of my beaker. And so this is the kind of thing I can do with this sort of problem. Or I could read it and I could say, hey, you know, I dissolved it to a saturated solution at 70 C. Let's say I do that with some potassium chlorate. At 70 C, I would have 30 grams dissolved there. Well, let's say I take that and I cool it down to room temperature, 25. Well, at 25 C, I cannot even hold anywhere near to 30 grams in solution. At 25 C, my full solution here is going to have like 9 grams in it. So I could figure out how much solid would have crystallized by looking at the difference between the 30 grams I could fit at 70 C and the about 9 grams I can fit at 25 C. So there'd be about 61 grams sitting at the bottom of my beaker. If you remember me recrystallizing our copper 2 sulfate at the beginning of the year, that's what I was doing. I would heat up the copper 2 sulfate, get it to completely dissolve, and then cool it down. And as it cooled down, it would move down that solubility curve, and the solid would recrystallize out and trap the water back into the crystal and turn it back into those dark blue crystals that we could dehydrate again. So a couple of other little things quick. We want to look at pressure of a gas and solubility. Changes in pressure have very little effect on the solubilities of liquids or solids in liquid solvents because liquids are incompressible and solids are certainly incompressible. However, it absolutely does matter for a gas, and you can absolutely see that anytime you open a carbonated soda. What happens when you crack open a soda? And bubbles. That is gas coming out of solution. So increasing the pressure by sealing that in the can increased the solubility of the gas and kept it in the liquid. When you crack open the can and it decreased the pressure, all of a sudden we saw that the gas would rush out of solution as bubbles because lower pressure meant there was lower solubility for the CO2 in the soda. You'll also note that if you ever go to a Coca-Cola bottling plant, Coca-Cola is bottled cold. And the reason they do that is because the warmer a liquid is, the less soluble most gases are. So if they bottle it when it's cold, then they can actually increase the amount of carbon dioxide that they're able to dissolve and trap in the liquid and in the can when they bottle it. This is also part of the reason why it's really important that fish tanks remain at fairly constant temperatures. Because if you've accidentally overheated a fish tank, you didn't actually, well, okay, most likely you didn't actually cook the fish. You actually smothered the fish because at the higher temperature there was not enough dissolved oxygen, and that is what actually causes the fish to struggle and possibly die. So these are some rules that we should definitely know. These are ones that we have talked about back in when we talked about precipitation reactions in the reactions unit, but just a couple of reminders. Things which are mostly soluble: group 1, sodium, potassium, lithium, ammonium, cations, and those are mostly soluble. Pretty much everything dissolves. Nitrates, acetates, and chlorates basically all dissolve. Chlorides, lead, silver, and mercury 1. Sulfates, aside from barium, strontium, and lead sulfates. These are things which will mostly dissolve. We saw ammonium chloride was quite soluble. We saw on our solubility curve our acetate, our nitrate, and our chlorates were quite soluble. Things which are mostly insoluble, and of course these are the same rules that are on your star chart: carbonates, phosphates, silicates, sulfides, chromates, dichromates, hydroxides, generally have the same set of exceptions. Of course, sodium, potassium, ammonium, several other ones that will dissolve with some of the calcium, strontium, and barium, but always you can bet on ammonium and the alkali metals being soluble. So I'm not spending a lot of time on these because these are on your star chart. Of course, you can use them if you need them. So you have just a couple more terms. Electrolytes versus non-electrolytes. Now, if you're an athlete and you've drunk some Gatorade, you've probably heard people talking about electrolytes. An electrolyte is a substance that dissolves in water that gives me a solution that does conduct electric current. If we remember that physicists consider a current moving charged particles. Hopefully it doesn't particularly surprise you that electrolytes are ionic compounds, because ions, by definition, are charged particles. So say salt, sodium chloride. Sodium chloride is absolutely an electrolyte, because if it dissolves, it will give me sodium ions floating around, dissociated and solvated in the solution, and Chloride ions, which have a negative charge, dissociated and solvated, and they can move in through the solution, and moving charged particles are a current. Now, a non-electrolyte is a substance that does not conduct an electrical current at all. So that means it cannot have charged particles. So things like sugar or glucose, those were soluble. But if I try to run a current through a glucose solution, I will not get a current moving through that solution because glucose is not a charged particle. So it will still taste sweet, but it won't conduct a current. So that is a non-electrolyte. A couple of other words, miscible versus immiscible. Those have to do with liquids. Liquids that mix or dissolve freely in one another in any proportion are considered to be miscible. So ethanol, for example, and water. You can't have ethanol until you are 21, but when you are 21, you will discover that you can get ethanol in water in any proportion between 3% and 97%. It mixes in freely with each other. If we think about that structure that we saw for ethanol and how it is a polar molecule that does have an H directly connected to oxygen, so it can have hydrogen bonding, kind of explains why that might be. Now, liquids that are immiscible are liquids that are not soluble in each other, like, Italian salad dressing. Oil and vinegar, they don't mix. Oil is nonpolar and hydrophobic. It cannot form any lower energy interactions with water. All it has is London dispersion forces. And so it would rather stay together with itself because it can't shove into that network of interactions between the water molecules. It's one of the reasons that you should never ever try to put out a grease fire with water. If you ever have a grease fire in your kitchen, you always want to put it out either by smothering the flames or by using something like baking soda, sodium bicarbonate, to put it out by smothering the flames. You never want to try to put out a grease fire with water because flaming oil will float on the top of the water and float out of your pan onto your counter. It's a really bad plan. Speaking of electrolytes, these are, I think, our last couple of terms we're going to look at today, strong versus weak electrolytes. Okay. Non-electrolytes are not weak electrolytes. Non-electrolytes do not conduct at all. Weak electrolytes do conduct. They just don't conduct as much. And it really has to do with how many ions or charged particles it is able to form in water. Most ionic compounds are good, strong electrolytes because they dissociate into ions into solution. But there are some ionic compounds that are weak electrolytes because even though they do dissolve, they do not completely dissociate. For example, acetic acid is what we call a weak acid because it generally actually dissolves as acetic acid molecules, and only a small amount of the hydrogen actually dissociates. Ammonia, NH3, well, you'd think, how would that form any charged particles at all? In fact, what it does is in water, it forms a very small amount of ammonium hydroxide. And so there are small amounts of ions in there, but not a very large amount at all compared to the overall amount of solute in the solution. So strong electrolytes will completely dissociate. We'll get 100% dissolved, dissociated ions that can move. We get lots of current, strong. Weak electrolytes, they dissolve, but they don't completely break up into their ions. So we get only a small amount of current, weak. So as I mentioned, a weak electrolyte generally does not conduct electricity as well And that's really because when we consider it, the bonds between the atoms are actually going to be stronger than the hydrogen bonds that solvate the electrolyte. So even though, say, acetic acid, which is down here at the bottom of the screen, it does ionize, but the solvation interactions are just not really strong enough to overcome the attraction of that acetate ion for the H plus. And so some of them ionize, but then most of the time that solvation interaction isn't strong enough to keep it from just snapping right back together. That is, as I mentioned before, different from a non-electrolyte. A non-electrolyte has no charged particles, none, zero, zip, non, none. Okay, weak still has some, non has none, strong has all. So I think that kind of gets the basic distinction across. All right, folks. So now we've got a bit of thinking about why some things will be soluble in different solvents. So you can use that to help you write up your conclusion for the solvent investigation and make sure you get that turned in. And have a great day, and I will see you later.